Hey guys, here I am tonight. Yeah, I got some stuff here today. Planned a little bit more. Got my Beija-Flor genealopolis, which says grass Beija-Flor de Nelopolis. And yep, we're like we're going live here, which is cool. Everybody always checks that. Make sure you got the little red dot. And there it is. I'm seeing signals all over the place. He's live. Of course, he's alive too. So for those of you who don't know, while I have wait for people to join us, I lived in Brazil, and of course, I have a samba school here in the United States. So what's a samba school? They're the big organizations that put on those incredible samba parades in Rio de Janeiro. And of course, they work all year on it. And those organizations are huge organizations where thousands, tens of thousands of people belong to a samba school or samba club. It's really, and they have a big place, and they have a place called the Big Tent, which isn't a tent; it's a big building where they make all their floats and all their costumes all year. And then once a year they compete in the Samba Drome, and this is Beija-Flor who won this year, 2018, in the Samba Drome. My samba school, Beija-Flor, means kiss flowers, and it has GRES, which Grêmio Recreativo Escola de Samba. So it's like the samba school. Beija-Flor genealopolis is the place where they are located. It's a city across the bay from Rio de Janeiro. And I see you're starting to get some people here. But so you wonder, I got all shirts. I love shirts. I got a ton of shirts. Got wear them all the time. So I got ones you'll see from samba. You're going to see other ones that I have that are from physics, from my hobby of physics and cosmology, and other things. But I get these from. Actually, I traded this shirt because I didn't go to Rio this year, and Beija-Flor is my samba school, the one I've adopted there. I saw somebody when we were at doing a big show, and we traded. It's like, hey, I'll give you one of my shirts for one of your shirts, and that's how I got it. So pretty cool. Welcome, one person. Today is going to be pretty cool. I just you noticed here I have a reason I have this, and it's because I'm going to be talking about the experimental and historical foundation of electricity. It's going to be pretty cool, actually, because it turns out that while we build these giant colliders that cost $1 billion or more, probably the most sophisticated machines maybe ever built by man, we don't even know the basics of physics, which is quite amazing. And I think that's why you have so many people outside the mainstream who are working, because we know we haven't answered things like, what's electricity? What's static electricity? What's magnetic fields? How does that all work? How does that interact with atoms and the atomic, subatomic structure? What's light? What's gravity? Those kinds of things. And we don't know. Meanwhile, we're pretending to find these particles. And if you haven't read the Higgs Fake, then you need to read the Higgs Fake. And they will you'll learn all about this. Let's see how we're doing here. I'm going to get on here, make sure. There it is, says me live, and I got one person. Oh, Lisa's there. Hey Lisa, let me get down to my chat. You and me tonight. It's great. I have 11 thumbs up already. I'm following along with the art tutorial tonight. Hey, cool. But the person doesn't talk. Don't worry. This is recorded. Actually, who's going to be really happy is going to be Professor Andrea Cease, who wrote this book. Let me get that on screen again. Let me move it up here. Andre K.T. Assis. He's a really great guy. I've known him for quite a while. And he has sent me a kit, which I'll show in a little bit when we get more people in here. So, hey, yeah, painting. Boy, I haven't done art. Most of my art I do these days is graphic art, because I have to do it for our physics group and also our Brazilian samba group. So I do lots of graphics, unfortunately. I don't do a whole lot of art, although I have done a few drawings as of late, pencil drawings, which I've framed for my wife of her mom, and oh no, that was of her aunt. So I did a drawing not too long ago, but I don't really do art, unfortunately. Man, I hope to get back to that. Let's see, if I emailed you a presentation at which many people spoke about anti-gravity, would you look at it or not? Absolutely, absolutely, no problem. Second question, can you tell me I'm on my computer and not using talk to text? Oh, that's pretty cool. My area is human language and computers, but I actually work in the area of getting computers to understand written language, because when you tell your computer something, it translates them to letters in the alphabet, and then of course it's got to understand what those are. People don't realize there's a whole phase to that. They think it's, oh, if I speak and it's got the words there, it's understanding. No, they're just letters, and so that's what I do. Let us thank a socialist from Labor Day weekend. I recommend Eugene V. Debs. Yeah, I think I've heard of him. But of course, we had a great victory here in Florida, and that's pretty cool. We had Gillum won, who is a people's person. He is, be shocking, he's a progressive. Hopefully he'll win here. Well, I see some more people have joined us. And it says, I will be listening and watching the tutorial, trying to... No problem at all. No problem at all. Like I said, I'm experimenting with this whole thing. Although I will tell you, I get a lot of views of this. I think it's because people are sort of listen to it, sort of sit on the side while they're working and doing other things and listening to the ramblings on, I guess. But maybe, am I getting enough volume here? You guys hearing this well enough? Hello, everybody. Make yourself known. Hello. I am here tonight to talk about the experimental and historical foundations of electricity. And I was saying, and I was talking to Lisa, I'll repeat that again. It's worth saying. And that is the Higgs particle, the Higgs boson, the Large Hadron Collider, which costs probably what, $1 billion, couple $1 billion, I don't know. It costs a lot of money, probably costs a lot of money to run as well. It's probably the most, well, it is the most expensive experiment ever built. And this is what we get out of it. Invented particles that we have that were not really found, or to pretend to be found, well, by two teams who pretended to find them, or to find the signals, as Dr. Alexander Unsker. Remember, don't believe any of this. Hey, don't take my word for it. Read this. I'm going to have to just talk about this one time. But regardless, what I'm making a point here is that I've got this little experiment here by Andreas Sies from his book called The Experimental and Historical Foundation of Electricity. And he sent me, and you can see it's made out of really simple stuff, super simple stuff. Tape, straw, plastic cup, some plaster of Paris, one of those folding thingy-doos. And this is by no means $1 billion. So my point is real simple. I'll tell you, end of the day, end of the week. Point is real simple, is that we don't understand even what's going on with this, let alone this idea that there's even a Higgs boson, which there's not, that there is even quarks, which there are not. And I know I have friends in my organization, the guy who we just, Dr. William Lucas, if you're watching this, I know you are a quark believer, but I am not. I think, yeah, it's symmetrical because they make those particles symmetrical. For those who are not into particle physics, what I'm saying is the particle collider in the standard model, which it isn't a model, but what they call a standard model, are a bunch of particles which they make symmetrical. And there's even a fight against symmetry. And there's actually, if you take a look at my videos, look up Dissident Science and Symmetry, and I will even talk about symmetry and what Dr. Alexander Unziger, the physicist from Germany, talks about it. But regardless, the whole idea is that we have these particle colliders, these atom smashers, the Large Hadron Collider, and all the other ones stand for linear accelerator, all of these things. And yet, we have no idea what electricity really is. We say we do, but we don't. We can try to describe it, and we don't describe even that very well. That's why Andreas Sies is writing these books. That's why Andreas Sies sent me this experiment, which I'm going to get to pretty soon. And so the story of the moral of the story is we're spending gobs of money on things when we don't even know what gravity is. We don't really know what light is. We don't know what magnetism is. We don't know what magnetic fields are. We don't know how electricity really works. We don't know how static electricity works. We don't know what charge is. We don't know what physical attraction is between positives and negatives. Although this is actually not true, because what I'm talking about is mainstream science. We, outside of mainstream science, are working on those things. And I talked with my father, who's traveling, visiting his sister in Indiana. I don't know if you're watching, Dad. Hello. You're probably not having as much fun as you should if you are actually watching this, but he says he tunes in once in a while. So my friends, hello to you. Hey, if you know me personally, you're around my area, give me a shout out there on the chats. But regardless, my father and I were talking about our particle model, and I came up with a fantastic, in the last month or so, to describe what we came up with. And this is what we came up with, and this is a technical term for those of you who know it, but in my opinion, the particle model is a Turing machine for the universe. Whoa, if you know what that means. And I think I'm right on that. We're going to start talking about it. We are writing, I will tell you a secret. Let me get to it before I bring it up on stage. Stage it to, I am going to wiki.naturalphilosophy.org, and I will show you that now. There we go. And I am going to go to, well, we're starting to put in theories in here. I just put in an info box for theories, believe it or not. What are info boxes? Those are all those, you'll see what it is. And here's the particle model. And this is in our Wikipedia. I've got it scrunched down a little bit, but you're seeing that we're starting to write it. So those of you who want to see it halfway and not done and all that stuff, it's there. Of course, you know, there's just millions of people reading this right now. It must be really frustrating for them. Not, well, the info box right here is for scientific theories. We have more than one because we are in a Kuhnian cycle of model revolution, which he says we will have various models competing, and that's what we have been doing actually for the last 400 years. So anyways, that's pretty cool. And I was talking with my father, and the reason I'm mentioning this is because I am going to talk about our experiment, or our, in this case, electrostatic detector or something like that. I'm not going to worry about the names because we're going to go through it in his book. And I'm going to describe what our model says about this to give you an idea, because it's really easy to sit there and say, we don't know about it, we don't know about it. But hey, as people say to me on my channel, and they say, congratulations, Dave, I like your channel, is because we come up with alternatives and answers to stuff. Sometimes the answers we don't know, but a lot of times we have an actual explanation. So thank you all. I see we have 7 people here. So let's start with our experiment here. All right, and let me explain this again, but I won't explain it because we can get it explained in Andreas' book. So, well, what I do, yeah. Andre K. Assis, right there. This is his book. I've got an electronic version. He was nice enough to let me have that. I don't think he's too interested in making money off of this. He's interested in being a critical thinker, being science woke on all this. And he certainly is a very interesting guy. He is very like my father in the sense that they concentrate on very basic things, but those basic things are very important because a lot of times we get into the super details like the Higgs boson and it's all malarkey. And so anyways, you can see Andre Koch Torres Assis, Institute of Physics from the University of Campinas. That's in São Paulo, Brazil. São Paulo, St. Paul, Brazil, which is a state and the capital of the state, St. Paul. São Paulo, as we say, or in English we say Sao Paulo, Sao, like a, but in Portuguese it's so, it's through the nose. We have nasal sounds in Portuguese. São Paulo. And Andre Assis is a professor there, and he actually teaches, oh my gosh, alternative ideas and alternative models to mainstream science, and he's still employed because probably people, they're okay because he's teaching things by Weber, Wilhelm Weber, I think, and who else? Ampere. Those are his two guys. And I've told many stories many times on this, but we're going to go down here. Now, he has sent me, let me go back to my, hey, there you see it? Here in my lab here. Oh, lab, it's my office. So what he sent me was this box, Correios, which means post office. And in that box, we got lots of stuff that he sent, including these little stands. You see, this is pretty cool. It's got, you know, those things that you sort of bend. There. Boing. Inside it's got plaster of Paris, we call it. They call it, I said, what's that? They go, cimento. And, well, you can hear what it sounds like. Cement. I go, everything's cement. It's like a more general word. But in here we have things that we're going to need, actually. Like, oh, straws. In here. Oh, we got one more of these. We've got a T format, T. Look at that. All these things, cork. And we will be doing only one thing tonight because I don't even know. I haven't done this, so this is pretty cool. So we're going to just look at this and go down here. Let's see if we can get down here to the start here. Amber effect. We're not going to do that. We're going to start with one of his apparati, and I believe that's in chapter 2. I think it's 28, page 28, 27, 28. Once I'm there, I will show you. Voila! So, electric instruments, a list of materials for experiments. We have a list here: plastic straws, an acrylic ruler, and a PVC pipe. Paper napkin and plastic bags, thin cardboard and or paperboard, paper and aluminum foil, tissue, the whole thing here. And so we will go down here, and we're going to look at the electroscope, the most important instrument of electrostatics. So they're talking about the electroscope, and here's how we start it. Again, we start out with one of these dudes. Right here, plastic cup. We get one of those pins, put it inside, and then we like fill it with wet gypsum dough. Whoa, they really did the translation, or what we commonly would maybe call plaster of Paris. So Andre Assis, if you're watching, maybe you can just use plaster of Paris, because I think that's what it is. It's sort of like a very light type of concrete, or cimento, sort of concrete, white cement, whatever. So, and with this stuff, we will make the following. I don't know why I'm yawning tonight. That usually they say it's because you're lacking oxygen. Well, that's not good. So here we go. I get this from Andrea Cease, and I thought, I'm going to have to build this. So I was all ready to build this before I got it. It's like, whoa, I don't have to do that because he already sent it this way. He sent it with tape on the back, and then this thing with glue, and then some type of strip here. I don't know if I have to get this off. Maybe he, let me see here. Nope, it's there. Okay. So it's all loose. It's actually loose here. I can show you. See? There it is. You can see it's loose. There we go. And so it sits there very nicely on my stack of videotapes because I can make it any height that I want, you know. So I've been digitizing old VHS tapes, including things from Dr. Chappelle. And so I see you are still there, and only Lisa has been saying things. Everybody else is like, okay, Dave, get on with it. All right. Anyways, this is electroscope seen face on. So we are seeing that face on. There's the face on of it. There's the back of it with the tape, and then the side view. You can see, of course, the cardboard and the little strip. The main components of electroscope. So I'm going to read this here. Thin cardboard and tissue paper strip behave as conductors in the usual experiments of electrostatics. And that says dry air around the electroscope behaves as an insulator. The plastic straw supporting the rectangle also behaves as an insulator, being the most important element of the electroscope. Oh, the straw. The straw. Okay. It prevents the discharge of the electroscope to the ground. Oh, so if we get charge up into here, right up into here, this will insulate it so that charge won't go to the ground. Well, what is it? Ooh, I'm going to explain it to you in the particle model. And I'm sure Andrea Cease is going to be totally fascinated or totally horrified. All right, we'll find that out. It prevents discharge. Okay, the plastic straw cannot be replaced with a wooden skewer or with a metal wire, of course. Those things conduct. So if a wooden skewer replaces that, the electroscope would always discharge to the ground after scratching its cardboard with an electric acrylic ruler. Electrified acrylic ruler. I don't know if I have one of those. Oh, do I? Did you send an electric acrylic ruler? Probably didn't. He probably says, get it yourself, Dave. What do you want me to do? Everything for you? Those are directions. He's probably sitting there, Dave, saying, Dave, I didn't send you one. Don't waste time looking at it. Oh, but I do see, ooh, this is like styrofoam. Maybe that would work too, because it's like really staticky. Okay. Therefore, it would be not possible to keep electrified after being rubbed. Okay. Comparison between a gold leaf electroscope and electroscope made with low-cost material. Okay, all of you here, please raise your hand and tell me whether or not you think this is gold leaf. Of course, it is not. And so, comparison between gold leaf electroscope and the electric made with low materials. Modern textbooks present the electroscope with discussing conductors and insulators, or when they present electrification by induction or polarization. They normally mention only the gold leaf electroscope. This has two mobile gold leaves which open when they are electrified. Yeah, I think they're like, I think I've seen that. It is extremely sensitive. Its strip of tissue paper rises easily. Oh, sorry. I got ahead of myself. These books usually do not explain how to make electroscope with simple and cheap material. However, the electroscope presented in this section works perfectly. Here it is. This is challenging, of course, the Large Hadron Collider in its importance in science. And in my opinion, this is way more important. Why? Because we got to understand this first, which we don't. We use all this stuff because we technically can use it. We have no idea what's going on physically. The strip is very light. It is fixed to the cardboard only with an upper end with a drop of glue. The remainder of the strip can easily move easily away from the cardboard without any hindrance whenever the instrument acquires a little amount of charge. The plastic straw is an insulator, of course, blah, 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 especially in dry weather. The main advantage of the simple instrument compared to the gold leaf is that it can be easily made to be teacher for the student. It costs almost nothing. Okay, good. A normal student will not try to build a gold leaf electroscope. Once in a while, I think the translation, they probably use Google Translation a lot and then have somebody look over it. Or Andre speaks very fluent English. A normal student probably, the average student probably. It's like abnormal student. In Portuguese, that's probably what it meant. After all, the instrument should be extremely expensive because it contains gold. This simple fact suggests that the device have been made by specialists, being difficult to construct, blah, 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 blah. Electroscopes and discovery of cosmic rays. In order to illustrate the importance of electroscope, we will mention here the discovery of cosmic rays. That's pretty interesting. For a long time, it was known that an electrified electroscope discharges slowly through the air. One of the reasons the air's conductivity is the presence of charged ions in the atmosphere. That is, the existence of mobile electrified particles. In 1896, Henri Becquerel, 1852, verified that uranium salts emitted ionizing rays, which increased air conductivity. Probably found it got cancer too. The gamma rays, high frequency electromagnetic radiation in particular, possess ionizing properties. They penetrate air up to a certain distance until they interact with neutral atoms, ionizing them. In order to research the original ionization of the air, the beginning of the blah, 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 blah. Dave, do you have any videos from Ricardo Carrizzani you can post? Gosh. I think we had a video. Dr. Carrizzani and his family probably have it, but I don't. Oh, man. That's a good question. I don't feel good about that as well. Also, is the society still functioning? Yep, right here. Me and my friend Amnon Myers. Dr. Carrizzani, I believe, is still alive. I think he's 98 years old. I haven't seen that he's passed on yet, but of course, I am his champion to the end. And a great man, one of the great scientists of the 20th century. Without a doubt. Bigger than Einstein because he figured out why Einstein was wrong. He had to undo a knot that Einstein sort of wrote. So, but good question, Tom, and I wish I did. Maybe sometime later on we can look into that. But I did have him photographed by a guy who photographed Einstein. So that's really cool. That was one of the things I hopefully did for history of science. And he certainly deserved that. Okay. Anyways, we're talking about all. So it sounds like they've got cosmic rays, and we're going to go past this because this is another one of apparati they're building, and another one still. And I'm not going to do all of these today. I'm only going to do this one because I just chose one. And of course, what we do with this, we'll find out. Pretty cool. Oh, our particle model really likes to work with electronics as well. Conductors and insulators. Classifying substances as conductors or insulators with the electroscope. Fractal truth. Hey, is that, are you who I think you are? Miss Fractal Black Holes? Oh yeah, Dave Tom. I saw Carrizzani's vids on Lucy Hayes' YouTube channel. Cheers. Absolutely. That's right. Thank you so much. In fact, I should maybe take a look at those sometime. Go over them in my video channel. So thank you for pointing that out. All right. Let's go forward. Okay, so basically, I think what he's talking about is classifying what's a conductor and what isn't. So let's read on this here. Briskly rub a plastic straw or acrylic ruler in hair or a piece of paper. All right, here we go. I'm going to grab a piece of paper here. And a plastic straw. Wait, I thought that was supposed to be an insulator. Here's a plastic straw that came with my kit. And let me get a piece of paper that's I'm going to cut down another tree. Where's a piece of paper that I can use here? I'm going to take notes on. Fractal Truth, yeah, I was asking you, are you your first name Lori? Okay, here we go. It's like playing about a cuica. I don't know if you know what a cuica is in Portuguese, but it's like it sounds like okay, so rub briskly. Okay. All righty. Very good. Oh, Fractal Truth. No. Okay. Well, I happen to know Lori Gardy, who's a member of our organization, and she is into fractals quite a bit. Check out her channel. So I'm going to do this briskly. After the rub straw has been removed, the strip stands off the scope. Okay, it says scrape the rub straw on the edge of the electroscope. Here we go. I'm going to, wait a minute. I'm going to do this way. There, see, so you'll probably be able to see it. And nothing. It's probably not going to get enough electrostatics. Let me try with the... We're not doing this. It's like, what's happening? Okay. Oh yeah, there. Yeah, okay. You can see it. Yeah, let me get it here. There you go. Boy, he thought of everything and made it so that you can see it. There you go. But the whole thing is I got to get a lot on there, and I don't think I'm doing it enough. Let's see. Oh, wait a minute. Maybe this PVC piping is better. No. Oh, he's got it sort of like all the band. Look at this. In this kit. It's got a rubber band, which they call elastics. Which I think sometimes people do call them in English. Elasticus. Yeah, is that what they call them, right? All right, let me try PVC pipe. Nothing. I kind of get it. He says ruler in hair. Okay, there we go. You know, it's really humid here in Florida. Ah. I see Fractal Truth. You're talking about who blew away Einstein. Is that Karazani? I'm going to keep trying here. So the idea is I'm supposed to build up charge here. It's not doing that. Maybe I need gold leaves. I think I just need to really be able to do this. Wait a minute. You know, it's like when you want electric static, you can't get it, you know. Hold on. trying to find how I can get static electricity built up here. I've got all this stuff back here. Come on. Andreas is going to send me an email saying, Dave, you did this wrong. This is how you do it. I just don't have, there's just not a lot of, I sort of feel, I do feel electro, come on, let's try it now. I mean, I know it has electricity on it, static electricity on it. Come on. I mean, you probably have to really go at it. He'd be able to say, Dave, you're just not doing it enough. It's just too humid here. Everything's discharging like crazy. It's going to find out that you can't do it in Florida because the humidity's too high. Although I do have an air conditioner here. But see, let's see. Okay, now it doesn't have any. Ooh. I wonder if I can try this. Seems like don't you like, I thought you could like rub up. This is not working out. I'm going to have to find out how to do this. This shows you what I should have done. Okay. I will definitely work on getting this done right so I don't get people bored to death on this. So here's what, let's talk about what is actually happening here, right? The idea is that you build up a charge. Let's take a look at what we're supposed to be seeing. Okay, there we go. And I should probably get one of those like acrylic rods and then really be able to do it. I think that's what I'm going to need to do. And I apologize to you guys. I'm going to have to find that out. But that's what this is all about. I'll come back next week with this because my whole idea is, sort of like, let's see. Oh, there it goes. But anyways, I'll work on this and make sure. I like to try to do things live. It's pretty cool. And then, of course, if you touch it, then it's supposed to go down. So, so here's what they're saying is basically he's saying is that you have a definition. We say that the charge electroscope losses electric. Okay, so let's go back here. We say the electroscope acquired an electrical charge due to the contact with previously charged straw, has become charged by contact or electrified by contact. This process is called charging by contact, charge transference by contact, or electrification by contact. Then, of course, when you touch it, then what happens is the discharging, by touching it, it's initially charged. Definition 3.2. We say that the charged electroscope lost its electrical charge by contact with the finger or with a discharged by contact. Discard by contact, electricity discharge, or simply discharge. The process is called discharge by contact, grounding, or earthing. Of course, that's what, we'll see that. It is also called electrical grounding, electrical earthing, to ground, or to earth. The origin of these names is the charged body is being discharged by a human body, which is normally electric contact with the ground. I'm sorry, the yawns are catching. Okay, so if you look at this is a little bit more of a, oh, wait a minute. I'm reading this stuff and you're not seeing anything, are you? Okay, hello. So there we go. So I'm so sorry. This is in his book, and there's the definition. Man, I'm just reading along here, and I'm not showing you. And there, of course, is when you have the supposedly negative charge, you touch that, and it's like moving out, and then you discharge it. And those are the definitions I'm talking about. And of course, I'm just I'm scrolling through this and not giving you any visual of what's going on here. Let me get this over here. Who knows? Maybe it all of a sudden become charged. Anyways, you can see this is when it is charged, and then when you provide a ground, that means a place for they say the electrons to flow. Then it goes down again. Touching, we present the most important experiment which has been made with electroscope. Hold one end of the body with the hand and touch the upper edge of the electroscope with the other end of the body. Figure. This shows nothing happens with the electroscope when the neutral plastic straw touches the cardboard. That is, okay, so touching the charged electroscope with a plastic straw. So basically what he's saying here is that if you touch it with a plastic straw, nothing will happen because it doesn't conduct. If you touch it with, it says, touching the charged electroscope with a metal wire, in fact, what will happen is you'll see that, in fact, it would go down. And I promise you, in fact, you know what I'll do? I'll make this into a video because I promised to do that and have it sort of made. My glasses are crooked. Made specifically, I told him I would be doing Andreas Cies, his experiments, which are very important. They absolutely are. The electrified electroscope is discharged when the piece of wool or metal held by the hand touches the cardboard. Utilize a rough wood in this experiment, that is a piece of wood that is not painted or varnished. So we can, what happens is you can use this to start testing different materials to see how good are they at conducting. Conductors for usual experiments of electric, humid air, human body, all metals, papers, thin cardboard, aluminum foil, tissue paper, pasteboard, wood, cotton, piece of chalk, many of these things. Main insulators as for experiments or electrostatics, dry air, natural resins like amber, and synthetic resins like plastic in general. And so he's going through that, and he basically just goes through and says, okay, we're going to just experiment around. Here's one, okay, it's charged, and we'll put it into, dip the edge into water, and we find that it discharges. So water conducts. Now if we put it into vegetable oil, like this, you will find out that what happens, insulating oil, like kitchen or vegetable oil, shows that that in fact, if you try that, it will not discharge. Conducting liquids, fresh water, rain, tap water, hydrogen peroxide, deionized water, distilled water. How about easy water? How about the fourth state of water, which is by Dr. Gerald Pollack, which I will be talking about his work sometime. Maybe I'll even interview him for my channel, just talk with him a little bit, but we'll be giving him the Lifetime Achievement Award for him discovering a fourth state of water, which is this water. Where can you find it? Get a glass of water and look at it, and if you see the water where it's lipped, you know where it's lipped. Let me go to my drawing. Oops, that's not it. There it is. So let me do this. I'm gonna, oh, I'm in the wrong one. There we go. Now if you look at the water, it will, the top layer of water, let's just call this a glass. And this is all water. If you look at this, I'm going to do it in yellow. If you look at this top layer of water, it's like a meniscus. You see right there on the edge, right here. It's got a curve on that, and you'll notice that. You've seen that, I'm sure. You can even put a coin on top of here, and it will float. Why is that? Well, because you have H320. There's the oxygens and the hydrogens. I believe that's how it works, but don't get me on the structure of it. But anyways, it's pretty cool. And that water forms this layer. They're sort of like sheets. You just keep going and hexagonal and keep going. And those hexagonals form sheets. And that's the fourth state of water, which is absolutely a fantastic discovery. So, where was I? I believe I was in the, oh yeah, talking about conducting. Conducting liquids, kerosene, milk. Oh boy, you gotta try all, they've tried all kinds of stuff. Acrylic paint, synthetic motor oil, or engine oil. Insulating liquids include melted paraffin and some kinds of oil. So that's interesting too. You can have tap water. You can see attracting a thin stream of water. So I promised to tell you guys, today I'm not going to go over 2 hours. For sure, not even going to get, I'm going to try to do this an hour and a half max here. But let me make sure I have any questions here. Pretty much blows the whole Einstein away. Fractal truth. Absolutely, he pretty much blows away. I'm just talking about Einstein. Okay. Ken Wheeler, his channel is Theoremosis. Check out Sometime Game Changer. Okay. So this is Ken Wheeler. Yeah, I'm gonna look him up and see if I've stopped yawning. Okay. Well, we're still not anymore. But we have 7 people here. That's totally great. Hey, I appreciate it, folks. My channel is growing by 3 a day. I know it doesn't sound a lot, but it's like 100 a month. That's pretty cool. It's moving along. It's picking up. So I really appreciate it. I'm getting lots of great emails now and then telling me how we need a channel like this, which is really cool. So appreciate it. So I promised to tell you, to give you an explanation. Let's see if I can go the right way here. There we go. All right. Give you an explanation of a physical model of what's really going on here, and we'll use the particle model. So I'm going to get my drawing out here again. There we go. Now I got to get myself back. All right. Keep this around because he's funky. Alrighty. So this is what we're going to do. We're going to look at something pretty simple. Let's take. Whoops. Come on. Here's an atom. Oh man. What the heck was that? This is a funny drawing program. Maybe I can just draw a circle then. Oh, cool. There we go. So this is an atom. Nope. I'm going to draw. What if I can make this bigger? Isn't there an undo on this? I guess not. I'm going to go to freestyle drawing again. It doesn't even have a good way to erase. There's not a whole lot of drawing programs that are out there that you do live that are really great. You just got to get used to them. So I'm going to do it by freehand now. Okay, here's the nucleus of an atom. And around this nucleus, we're going to call the orbiting particles. Okay, they're called electrons. In mainstream, we call them G1 particles. In our particle model, that if this is a hydrogen atom, you have 1 nucleon. We call them a nucleon because in our model, we do not have charge. These things are kept in orbit just like gravity is, but it's G2 gravity. It's a gravity level down. with small particles that do that. So those things are orbiting. Just imagine it's just like a sun. But the thing is we have lots of them. So the difference with our model is there are lots versus one. Now, one of the reasons you may ask, why is that? Well, it's because if you look at the periodic table, we do not have increments, exact integer increments of electrons. That's funny. Why is that? Well, because this is my belief is that we have G1 particles, lots of them, these little particles flowing around. That's the right there. So if you have lots of atoms, you have G1 particles flowing around, and these are very stable. Not always very stable, but most of the time they're very stable, especially if they're like hydrogen or something, and oxygen. Those things are very stable, copper, those things. And what keeps these things together are flows. Lionel Denis to the rescue. And that is, there's a flow this way. Flows of particles attract and repel. Look up Lionel Denis. And see that you will see that's what it is. That's what part of the inspiration of this, one of the aha moments when I saw his stuff. So we have that. So imagine this is a wall. This is a straw. Okay, let's make it a straw. So this is a straw. And what we're going to do is to rub something on that straw. We're going to rub a piece of paper. Here's a piece of paper rubbing on the edge, these two edges. Oh, make it purple here. Purple straw. Now what happens is, in the particle model, what happens is you have lots and lots of G1 particles, are very stable. Those flows keep these together. Of course, if you know anything about atomic structures and molecules, those molecules have what they call polarity. What does polarity mean? Well, we give them charge. We say the reason this proton, they call it, we don't call it proton, we call it nucleon because it's not charged, attracts and keeps these electrons there is because you have a negative and positive. They never tell you what that is. We tell you what it is. It's a gravitational field, one below. It's below the gravitational field that we have here. So it keeps going around. So what happens is when you rub these molecules with their orbiting stuff on it, you are rubbing these together, you're getting interference. What are you doing? You are disturbing the G1 particles, or in this case, if you want to call them, electrons. Again, we don't like to call them electrons because that makes them electrically in charge, and they're not. They're just particles. We call them charged and all that because we don't have a mechanism, but we do. So just like the gravitational field, these are G2 particles that are flying at c squared. G2 particles are flying around c squared in all directions. Those keep these in orbit. But if you disturb them, if they hit each other or whatever, they will be disturbed. Then guess what happens? These G1 particles, and I will put them in red. I believe this is red. I'm sort of colorblind-ish. These G1 particles can start flowing not in their stable area, but in different areas, so that you would disturb them. It's just like if you were going to rub two solar systems together with lots. Imagine asteroids, lots and lots of them, but just going at a super high rate. Those things, when you bring them together, now you've disturbed them. Those G1 particles get out of orbit and start just orbiting around. Eventually, they will fall back and either be lost into space, or they'll be captured again by the nucleons and settle down. This is what happens with this apparatus. So what happens is I take the straw here, and they're made up of nucleons or nucleuses or protons with electrons, and I rub it. I am physically smashing these things together, causing the disturbance of these flowing particles around nucleons, and that puts them in orbits around the whole thing. You start getting literally fields. That's what a magnetic field is. A magnetic field is the same as what goes around the nucleon. It's just that the nucleon holds these in stable orbits at tremendous speeds, c. But when you make that disturbance, you're making a physical disturbance. It now has G1 particles flowing around, which if I touch it, it conducts into my finger, because the way things are conducting is because conductors have a configuration of here we go. Conductors. No, it's not a good pointer. There must be a pointer here. Pen hand. Oh, there we go. Yeah, there we go. So conductors will, if you touch something, are those things that will easily drain those off. So you can imagine that the nucleons are set up in a way that will channel these things. Now, this is somewhat similar to, well, not really, but somewhat similar to the idea that of ether 1, 2, and 3 with Borkert. But this, I think, has a lot more physicality to it. So basically what happens, and what mainstream science has no explanation for, they call things charge, they call things positive and negative, they talk about attraction. We say there is no such thing as charge. What we have is a force, and that force is caused by a gravitational field. And just like Andrea Cis says, that the gravitational field comes from stars. Well, what is that? Well, stars shoot out two things. They shoot out G1 particles or electrons. They also shoot out nucleons. And that's why we get mass increase in the Earth, because those things get put together again inside of the Earth. But regardless, what I'm saying is, in our model, all we have here basically are nucleons and G1 particles, and their forces to keep them together are leveled down, just like, imagine all the atoms are solar, or the size of suns and comets and those kinds of things. And so therefore we have this explanation, so that what happens is when I rub this, I dislodge electrons or G1 particles. When I touch this, what happens is those things that are flying around will be conducted through the atomic structure of these things, literally flowing, and that causes it should be acrylic, right? I think that's why I'm not getting. I'm just thinking why this isn't discharged. I'm doing it with a straw, which is an insulator. How stupid can I be? But I thought he said straw. Anyways, what I'm saying is that in our model, basically, you're disturbing flows of electrons or G1 particles. They get conducted in here, and those things are flowing. They set up flowing in this. They set up flowing in this. We can explain to you why this goes up. My dad has some videos on electrostatics, and the reason is because this thing has a physicality of a long kind of thing, which will have G1 particles flowing around it. The flow will cause it to move out, because it will be flows, again, Genovo, I would say, Genovo. cause that. So the electrostatics, I'm not going to talk about that. That's a little bit harder. But the idea is what you do when you take a balloon like this. This is not a balloon. You rub it on your shirt. You're dislodging G1 particles. Those flow around outside of this. So when you do this, what's happening physically, or when you rub this, you are taking electrons, or you're taking G1 particles. There are more G1s than electrons, and those are being dislodged. They set up flows. Those flows are dictated by the atomic structure, which is really, atomic structure is 99% of it in mass is the nucleon. How those nucleons are set up, and those nucleons are set up because the nucleus is actually like in oxygen, you have 8 nucleons, and those are set up probably in we think in a tetrahedral form, where they're just spheres and they sort of stick together because of the G2 particles. And because of that, you dislodge it, sets up a flow here. I then stick it to something. That flowing on the balloon causes the Yonel-Deneau effect of attraction, because it will set up a flow on the surface. Those two things will be going. So when that flow gets close to a wall, the flow of those G1s causes a flow in the wall of G1s to dislodge. Those flows will go on for a while until eventually they're either flung off or they get reincorporated into the atomic structure, because again, even a hydrogen atom has more than one electron, we call it. They're G1 particle. There are a lot more of those, and there's good reasons to think of that. Periodic table is one of them. So that gives you an explanation of how our model would describe this kind of setup. And again, electrostatics and why this one goes up, it's a little harder. But our model, as I said in the very beginning, is something that I just came up in the last couple of weeks. What our model is because it's all particles, all particle flow, and it's infinitely down and infinitely up. All particles are made of particles. You have gravity at our level. You have gravity, which is the, you would call it the strong nuclear force, but that's just G2 gravity. That is just another field of gravity. Below that, you have G3 that make the G2. You have atoms. That is a nucleon. Is made up of another set of atoms, which is a different periodic table. So P1 is our periodic table. We have P2, which is a periodic table below, and it's probably a whole different kind of set of particles. In this case, we call them atoms. This model is being able to describe light for us, magnetism, gravity, atomic structure, electrostatics, electromagnetics, also the double slit experiment. We can explain exactly why this goes on, and it even explains dispersion being the rainbow, and why that is, which is pretty amazing. It took us about a year to hack that. And so we have a Turing machine model, which is just particles moving in straight lines until they hit each other, bounce off, or are captured because of the fields. So anyways, why is this important? Why am I even saying this? It's not because I'm trying to make you all believe that the particle model is the correct model. Maybe it'll be a model that will be accepted someday, maybe not. It's one of the models being suggested out there. My father and I sort of stumbled upon it by putting things together. We didn't invent it. The only part my father did was the light part of it. And so what it allows us to do is this electronic circuits. My dad is doing parallel resistors right now, which, believe it or not, a lot of the explanation of how they work isn't even inside the resistor itself. That's the flow of G1 particles are actually outside. The same thing with a battery. A battery holds electrons, or we call G1 particles, and it actually, if you put a compass next to this, it has a magnetic field. And that field is outside the battery. So batteries hold, of course, chemically G1 particles or electrons inside the the atomic structure. That's what, whatever we make batteries out of, that's why they're good at it, and that's why we try to make batteries out of better and better stuff that holds more electrons or G1 particles. But there's flowing outside. Now that makes total sense, because when I take my Apple Watch here and on the back, and I put that onto a charger, let's call it this here, how in the heck am I charging a battery with no real physical connection? That's because there are G1 particles flowing, there are electrons flowing outside of it. And so that's how we can charge things, and so batteries have that. Our particle model tells us that. The Large Hadron Collider doesn't tell us that. The Large Hadron Collider is something that the physics community put together to, and I actually call it, let me see if I can find that. I'm going to find that for you. It's definitely worth going and showing you. So before I say it, I'm going to let a meme say it. Please feel free to use our memes. I mostly made them, but that's okay. Wow, no more questions still. Oh, we got 5 people holding on. They probably go, that's it, Dave? Okay. There we go. Our science. Now I can go to memes. Stop that. Darn it. I'm going to have to make it bigger here so I can get to it. Our science. Memes. Here we go. And then I'll bring that in. And I'll be able to show you that. See, I'm getting better at all this. There's some memes that I have come here. There we go. Great meme here. Right here. Here's a picture of, oh, you can't see I thought you could see the mouse. There it is. There you can see the mouse. There's a picture of a meme that I made a while back, and I thought this was a pretty good one. I like coming up with sayings and memes and all that stuff. The world's most powerful, and you're of course expecting particle accelerator, because this is the Large Hadron Collider where they allegedly found the Higgs boson. But I said, the world's most powerful Nobel Prize machine. Absolutely it is. So that's what I would say. Anyways, I think that's pretty much it for tonight. I know I don't see very many questions. I think people are just hanging out, listening, so painting, doing what they want. But I think this has been a good session. I did try to do this. I am going to definitely work to see if we can get this electrostatics. And what I really want to do is maybe even break this into 2 parts, where I have explain this and make this actually work, so you can see this thing work, as Dr. Andreas Cease said he'd like to see this work. Of course, that's what he built it and sent it to me. Here I go again. My goodness. Sorry, Lori. And then basically I then explain electrostatics with the our particle model, to give you one example of how a model would actually describe it. Hey, there's somebody soldering up some electronic projects. Hey, he's coming in now, must be. Or maybe he's just coming to life. Oh yeah, he was in here because I don't see any change in the numbers. So yeah, absolutely. This is, but my dad is actually doing some, yeah, stop the yawning. My dad is actually doing some circuit boards, which is pretty interesting. I'm going to try to have him, maybe I'm going to go over for his Particle Guru, and I suggest you guys, if you are not subscribers to my father, he is very well organized, has really great slides, plans his stuff in advance, not like me, who just flies off the cuff with all this stuff. So, but anyways, I hope you understand. Again, the big thing is, Andreas Cease is absolutely right. We have to get back to these basics to be able to describe that. That's what my father and I are doing in the particle model. Again, I'm not here to say it's right. What I'm here to say is that's the right thing to do. And the right thing to do is to make models and physical models of what we see. This idea that charge, the magical plus and minuses that we write on these things, that all of these things that, oh, this is negative charge, I put it here, and then the negative and positive move away. Well, it turns out that we have to eventually come up with the physicality of that. And that's one of the things I will be making one. I have these things in line. Why am I always talking about physicality? The simple answer to that is because we are tired in science to not have physicality. Space, time, and quarks, which are just circles on a page, and attributes, which are just words, literally, and symmetry, which we insist on making, whether or not that's true or not, when it actually Glenn Borchert says to us that all particles are different. There's no two electrons alike, just like there are no two people alike. There are no two particles in the universe that are identical. Absolutely wrong. Not. So those kinds of, the idea again is that we got to stop with spending the huge amounts of money on boondoggles, on inventions, on Harry Potter worlds, on unicorn worlds. Basically, when people say, what are they doing if this isn't real? Well, I say that basically what they're doing is they study unicorns. They study the mating habits, the migration patterns, the digestive systems, the eating habits, the families of them, and the different genuses and families and whatever you call those things in biology. There's only one problem. They're fake. They're not real. They're fantasy. So that's my spiel for today. I will open up for any questions, but I see people are sort of dropping off already because I assume that they're saying, okay, he's done for the night. I'm 1 hour and 17 minutes in. So if you have any questions, good, yes, agree, no two particles can ever be identical. That must be true. Cool. Good. I don't know who you are. Are you? My question to you: helium, xenon, krypton. Are you? Do you read Borchert? Do you know Borchert's work? Now I know it takes like 30 seconds sometimes for this stuff to get out there. But again, any questions before I go with my Beija Flor Nilópolis? Hey, I don't have any of my Brazilian friends who said they were going to be here and they wanted to see me do this. So, hey, Brazilian friends, I know you probably are watching this afterwards, but I will even put up a new graphic tomorrow stating that this is about electricity, doing Andrea Cease stuff, so that way people will know. But if you guys have no more questions and people are dropping off, I will see you guys later. I'm going to go watch a musical with my daughter, who is an actress person. Never heard of Borchert, just a random math guy. You need Borchert. Look him up. Glenn Borchert, B-O-R-C-H-A-R-D-T, I believe. D-H-T, perhaps? Glenn Borchert. Got to read him. He's right up your alley. So I'm a mathematician myself, so absolutely. Alrighty. So let me put that, I'll even type that in for you. How's that? Before I go. Glenn Borchert. I think that's how you spell it. And get his book, the latest book. Just get that one, the Infinity Universe Theory, I believe it's called. UFT. Okay. Well, thanks a lot. And remember what I always say, stay critical, stay thinking. Don't take my word on it. My name's David Hilster. I am your science therapist. Thank you all for showing up tonight. Ciao for now.